In May 2016, a crude oil tanker arrived in Port d'Antifer to discharge 1.9 million barrels of Bonny crude oil. After being given the go-ahead to start the discharge, the cargo officer flooded all 3 cargo pumps by opening number 1 center cargo tank main suction valve fully, as required by the discharge plan. Number 1 center cargo tank was 98% full and a full bore of crude oil suddenly impacted the walls of the pump casing. Having travelled 250 meters along a 750 millimeter diameter pipeline, this violently jolted the pump assembly and the fittings connected to it. The officer in charge heard a slight shudder, but as this happened every time he flooded the pumps, he thought nothing more about it. But he didn't know that the pump suction pressure transmitters were always failing on number 1 and number 2 cargo pumps, because they were being flooded in this way. More worryingly, on this occasion, the impact had dislodged and weakened a suction pressure gauge pipe on the pump. As the officer in charge knew nothing about this, the rest of the cargo tanks were opened to the pumps and discharge continued with the pumps at full speed. When the tanks were close to empty, the pumps suddenly became very noisy and the pump discharge pressure gauge readings fell. This indicated that it was time to stop number 2 pump, as per the plan, and slow down the other pumps as the tanks were nearly empty. Unfortunately, cavitation subjected the already weakened pressure gauge pipe to sudden vibration. This was enough to make it shear and spray crude under high pressure all over the port side of the pump room. Throughout this module, we'll learn how these types of accidents can happen. More importantly, we'll learn how they can be avoided. During bulk discharge operations, centrifugal cargo pumps are an essential component of a cargo system. However, without knowing how they generate flow and pressure, it's difficult for those controlling discharge to appreciate how to use cargo pumps effectively. Some tankers are able to discharge at rates of up to 18,000 meters cubed per hour. This is the equivalent of filling 6 standard 20-foot shipping containers in 1 minute. That's 1 every 10 seconds. When considering such high flow rates, it's important that those in charge of a discharging operation understand how to control the centrifugal. We'll start by looking at the relationship between discharge pressure and flow for different pump rotational speeds, and then we'll consider how a cargo reception facility arrangement affects pumping rates. We'll also focus on how to operate centrifugal cargo pumps effectively, and how to operate pumps as cargo tanks approach stripping levels. Throughout, we'll use this pump control console to show what you need to monitor and control during the discharge operation. We'll also consider some of the practical aspects of controlling flow rates so that you can play your part in a safer, more efficient discharge operation. Centrifugal pumps are used on crude oil tankers for the transfer of ballast and cargo, as they can develop large flow rates. Let's take a look at how centrifugal cargo pumps work. As crude enters the pump, the rotating impeller speeds up the liquid. The crude then slows down as it passes through the narrow part of a spiral funnel-shaped chamber, called a volute. As the area of the volute increases, so does the pressure of the crude, which results in the crude leaving the pump with increased pressure. If you are to control the flow of crude oil cargo correctly during bulk discharge, it's important that you understand the relationship between the flow and pressure generated by a centrifugal pump. When considering the pressure generated by a centrifugal pump, it's useful to think about how far up a column a pump can lift a liquid. Pumping system designers and manufacturers refer to this as head, or more accurately, discharge head. This is usually measured in meters, but can be converted to the more familiar unit of pressure, known as bar. We do this by multiplying the head by the density of the liquid being pumped and dividing it by 10197. For example, A head of 155 meters and a density of 890 kilometers per meter cubed would be equivalent to a pressure of 13.5 bars. How the head changes with flow is a characteristic of a centrifugal pump, and this relationship can be shown on a graph. Here, the x-axis represents the volumetric flow rate in meters cubed per hour. We give this the letter Q. The y-axis represents the head in meters. We give this the letter H. The maximum head that a pump can generate occurs when the flow is zero. We call this the shut-off head, and it is equivalent to what would be seen on the pump discharge pressure gauge if the valve was closed against the flow. The maximum flow occurs when head is at a minimum. This would be the case if the pump flow was totally unrestricted. Between these 2 points, there are a range of head conditions with corresponding flow rates. Pump manufacturers create the range of head conditions by throttling the pump discharge valve under test conditions and recording the various flow rates. The result plotted on the graph is known as a pump performance curve, or sometimes an HQ curve. You will see this in the pump manufacturer's handbook, and they will often be posted in the cargo control room. While it is theoretically possible to operate the cargo pump under the full range of head conditions, you should avoid operating the centrifugal pump close to the shutoff point because the flow rate is very restricted and the pump casing could overheat. You should also avoid operating under very low head conditions, as the huge flow rates generated can cause a large torque on the pump shaft. There will be a point where the pump is developing flow and head at maximum efficiency. This is called the duty point, and this is the point at which the design discharge head and flow rate meet on the pump performance curve. 4,500 meters cubed per hour flow rate and 100 meters head. Using our formula from earlier, we can work out the flow rate by multiplying the design flow rate by the given pump rotational speed divided by the design rotational speed. This gives us a flow rate of 4,500 meters cubed per hour. Similarly, we can work out the head by multiplying the design head by the pump rotational speed divided by the design rotational speed all squared. This